Welcome back to ECE 501B. Homework number 2 is due on Wednesday, and homework number 3, which I need to post, is due not the following Wednesday, but I think the subsequent Monday in a couple of days prior to exam number 1. So exam number 1 in this class will be on a Wednesday, and material for that I hope is on D2L, and hopefully shortly homework number 3 will be available, but I'm assuming you're still focused on homework number 2. Today what I want to do, if my finger will work too well that time, is to continue with chapter 3 material, and chapter 3 is dealing with linear maps, and the linear map is operation, well, I shouldn't say operator because we'll be very particular with that word usage. So that will only be a special set of these linear maps. But T is maybe what we will use to refer to a linear map, and that will go from some domain V to a codomain W. And what we're doing in that domain and codomain is what we're learning about today, as far as how much of that domain are we living in and how much of the codomain are we living in, and that's related to these notions of null space and range space. We'll talk about a null space, give its definition, and show that it is a subspace of the domain, the vector space V. Then we will talk about an injective map, which is a one-to-one map. There's a lot of n's floating around, and that is nice because that's connected with null space. So that's why I've underlined null space, the n in null space and the n in injective, to try to make that connection. Then we will talk about a range space, and that now is worrying about the codomain, or the W vector space. Where do we get to? What's the range? What's the image of this linear map? We'll provide its definition, and then we'll simply state that that's a subspace of W. Then we will talk about a surjective map. A surjective map has an R in it, which is convenient, and we'll use that to try to help us remember that surjective maps are related to range space. And a surjective map is an onto mapping. It fills all of W. So we have injective maps and surjective maps, and they refer to two different vector spaces depending on what the linear map is doing. And then we'll talk in general, or more general terms, about maps and dimensions, and then we'll start thinking about matrix representations of these maps. We don't always have to have a matrix representation, or if we do, what does that look like for these linear maps? So let's now start by looking at the null space. And the null space of a linear map is the subset of the input space that maps to the 0 vector in the output space. So the null space is dealing with the domain's vector space, which is V, and that is then the subset of the input space that maps, and here we're saying the subset, and we'll subsequently show that it's a subspace. But here we're just saying it's a part, a piece of the input space that actually maps to the 0 vector in the output space. So what vectors in the input space map to the 0 vector in the output space? That subset is what's called the null space, or those vectors live in the null space of that linear map. So here's what we can say. Given, and this is definition 12 in chapter 3, given a linear map T such that T takes the vector space V and maps it into the vector space W, then we can talk about the null space of that linear map T, or I might, instead of writing null, I may just abbreviate that with this script N. That's now the null space notation, which really says that that's all of the vectors little v in big V in the domain's vector space V, such that if we map those vectors V through the linear map, they map to the 0 vector in the output space. So this set of vectors in the input vector space V that map to the 0 vector in the output space, those V's that form this set are the null space of that linear map T. And obviously we could think of this in the form of a picture. So if we have, and now we're back to the clouds. So here is our domain, and here is our codomain. And let's say that we have a mapping T, and these are all mapping to the same 0 vector Z in the codomain, but they may actually be taking different vectors V in the domain. So this set of vectors in the domain that map to the 0 vector in the codomain, that set of vectors is what we are calling the null space of that linear map. So here is the 0 vector in W. Yes? So the codomain, the reason why I'm not saying range is because the codomain is the vector space that the range lives in. So the range doesn't necessarily have to fill up the codomain. So we're basically saying we have a domain and we have a codomain, but when we speak of the range, that's usually where can we get to in the output space. So you could think of the domain as the input vector space, the codomain as the output vector space. But we're careful not to necessarily just use range, because that could be a restricted vector space in the output vector space. So we're just going to call it the codomain. Does that help? So let's now look at some examples of null spaces. And we'll start with one that's not really associated necessarily with what you think of as far as a matrix. So now the differentiation map. We've shown that that's a linear map. Now let's show that T, if that's the notation that we're using, that takes polynomials over the field of reals into polynomials in the field of reals, then what is contained in the null space of this differentiation map, where the null space of T is, again, spelling it out, and I'll probably quit doing that subsequently, but that's now all these polynomials P, such that when they're differentiated, you get the 0 vector in the vector space of polynomials. And now, can you think of polynomials which, when differentiated, give you 0? So now if you had a polynomial that was a constant, that would be in the null space of this differentiation map. So you could now say, oh, the null space of that differentiation map is the set A such that A is real. So you give me a polynomial that's a constant, and that's in the null space of this differentiation map. And you're going, well, that doesn't look like a polynomial. Well, make it a polynomial. X to the 0. And typically we don't even put that there. So there is a polynomial. It's a constant. It's a real number. Pi. You differentiate pi with respect to x and you get nothing. You give me a pi, you won't have much left after a few minutes. So I'm the differentiation operator when it comes to that constant. Okay? Sorry. But I had to wake you up maybe, and maybe I won't hit the floor in this lecture like I did this morning, and that never mind. Let's now, and I'm not going to change dimensions. Here's another, but this is an operator that we will use, dimension changing operators or linear maps. And suppose now that a dimension changing map T is such that we go from R3 to R2. Here's a linear map that goes from a three-dimensional real vector into a two-dimensional real vector. As an example, suppose we now have those three coordinates in the input vector space capital V denoted by x, y, and z. So now you could think about this room as the input vector space, x, y, and z. And now we're saying that based on that, we're going to map to a two-dimensional space. And that space is going to be given by 2x minus y plus 3z for the first coordinate. That's a function of the three-dimensional location. And now we map to a two-dimensional first coordinate. The second coordinate is 7x plus 5y minus 6z. And now we are interested in what points x, y, z in this three-dimensional volume actually map to the 0 vector 0, 0. What points x, y, z actually are a subspace, we haven't learned that yet, but a subset of vectors in this three-dimensional volume that actually map to the 0 vector in 2 space. What does that mean? Or what points x, y, z that belong to R3 map into 0, 0 in R2? So here's the 0 vector. And what do we see that might do that? I mean, it may be very easy to see, oh, x equal to 0, y equal to 0, z equal to 0. That'll work. But is it bigger than that? In this case, what do we need x, y, and z? How do we need them to behave? Well, we need 2x minus y plus 3z to equal 0. And at the same time, we need 7x plus 5y minus 6z to equal 0. So we need x, y, and z to satisfy 2x minus y plus 3z to equal 0, and at the same time 7x plus 5y minus 6z to equal 0. That's the condition for this null space. Or we could say the null space of T is actually the set of 3 vectors, since the null space is defined in the input vector space in the domain. That's these 3 vectors, x, y, and z in R3, such that 2x minus y plus 3z is equal to 0, and 7x plus 5y minus 6z is equal to 0. We need both of those simultaneously to be true. And it can be shown that the null space of T actually is the span of the following one vector. It's minus 9 over 17, 33 over 17, and 1. And if you're not seeing rational numbers too cleanly right now, let's convert those to decimals so that we can kind of see what in the world this really represents. But this now represents a line through this three-dimensional space, where in terms of relationships between the coordinates of that line, the z vector, we're going in one step, 1 unit of distance, for roughly 2 units in the y, 1.94, so 33 is not quite 34, so we're just a little under 2 in the y direction. And minus 9 over 17, that's a little bigger than a half. So now we have a minus 0.5294 in the x direction. So if you can move proportional to those 3 numbers in your 3 space, anywhere on that line will map to the 0 vector. Yes? How do you find those numbers? This is where you can go home tonight and perform your row reduction, right? So this is the linear algebra piece that we're not going to go through, but you should convince yourself that I did the algebra correctly. So you have 2 equations in 3 unknowns. So now you need to find what combination of x, y, and z will give you 0. So now if you put this into so what is row reduction? Well, if you put this into a equation, let me see if I can get the numbers right. 2, minus 1, and 3, and 7, 5, and minus 6. That's how you could formulate the linear algebra type problem, and now you can row reduce. Are those 2 rows linearly independent? It looks like it. It doesn't look like they're a linear combination, but you can now find a relationship between x, y, and z by saying, oh, let me get the bottom row at least as close to 1 element or 1 entry as possible, and then back substitute. Let z equal to 1 and then see what y has to equal and what z needs to equal. But there is obviously a combination of x, y, and z that will allow you to map to 0, 0. Okay, so I won't go through that here, but this is really the way to go about that, or one way to do it. But it's two equations and three unknowns, and you now have some flexibility in those three variables to map to 0, 0. What's another dimension changing map that has a null space? So this null space was one dimensional. It's a line going through 3 space with this ratio of x, y, and z, that relationship. Another one, let's say t, such that R3 is taken to R5. Again, we're looking at a 3-vector, x, y, and z, such that minus x plus y minus 3z minus x plus 2y minus 4z, x plus y plus z, 2x plus 3y plus z, and one more relationship, let's say, is x plus 2z. And now what do we need? You could hopefully see how to factor out x, y, z if you wanted to, but what do you need to happen relative to the choice of x, y, and z? Where do you need those to eventually end up? You need them to be in a 5-vector of all zeros, right? So you want x, y, z mapped through t, and this is the mapping. This tells you how x, y, z combine to give you each of these coordinates in your 5 space. And now you say, is it possible? Hopefully you can see that if you set all of these x, y, and z to 0, that you definitely have all zeros. What else? Well, that may be needing some analysis. But we really are saying then that we need the right-hand side of this mapping to equal this 5-vector. For some vector v in R3. And you can go through something similar to what I had explained before and actually find out that, in fact, this does have what I will call a non-trivial null space. A trivial null space would be the 0 vector. That's the trivial null space. When I say a non-trivial null space, that's when it's something other than the 0 vector. So this mapping, this linear mapping of t, actually gives you a non-trivial null space where the span is now -2, 1, 1 in terms of the combinations of x, y, and z to put you in the null space. If you plug in -2 for x, y equal to 1, and z equal to 1, you will find that this map goes to 0, or any linear combination of -2, 1, and 1. That's what this span means. But that means we're living on this line that's determined by this combination of x, y, and z. Now in this particular case, this is really sort of a cooked up example because our codomain's dimension is bigger than our domain's dimension. And typically when that's the case, you have a trivial null space. Here it was cooked up to have a non-trivial null space. But generically, if you just randomly selected a linear map, you probably would have a trivial null space when you're going from a lower dimensioned vector space to a higher dimensioned vector space. So note that the dimension of R3, which was equal to 3, is less than the dimension of R5, where this was our domain and that was our codomain. So it's by default, when your domain is bigger than your codomain, you're going to have a non-trivial null space. This one, you kind of have to have a particular combination to make that happen. So this situation is typically where this situation, I'm meaning where the domain is dimensionally less than the codomain's dimension. This situation is typically less likely to produce or to have a non-trivial null space. So those are some examples of null spaces. We have a differentiation map. We have these dimension changing maps. Let's now start talking about null spaces and their properties. So proposition 314 says that the null space is a subspace. And in the textbook, sometimes these proposition he labels. So this is the label, and now we'll sort of explain or define or create this true statement. Question? So the reason I say it's typically less likely is now you're going from something, let's say a 1 vector into a 3 vector. So now to get to 0, 0, depending on what you randomly have in that map, it may not be as likely to map a combination of variables into. So now if you had, let's say, 6x and 7x and 25x, how are you going to get all of those to equal 0 simultaneously? The trivial case. So it's typically, unless you have some sort of special situation, it's less likely for a linear map that takes a smaller dimensioned domain into a larger dimensioned codomain to have a non-trivial null space. That's all I'm trying to say there. Yes?
Yeah, and then if that was the case, when you have to verify the transform, was it went from R3 to R4 or something? You know what I mean?
So now, in this case, it's pretty clear where you're going. But in general, maybe it's, so the question was, do you have to sort of determine or verify where your codomain lives or what the vector space is? And yes, we'll have to basically know that for these linear maps in order to sort of talk about what is the 0 vector and what's it going to take for us to get there from the domain. So here, the null space is a subspace. That's basically the label on proposition 314. What that says then is just another restatement underneath that. But this is sort of the abbreviated title of proposition 314. 314 says that the null space of a linear map T such that some domain is taken into a codomain, a domain V is taken into a codomain W, is a subspace of V. And now how would we show that or prove that is a true statement? What do we know about subspaces? Or what properties do we have to show? They have a lot of properties, but what was sort of our strategy for dealing with subspaces? We had three properties, didn't we, that we needed to verify or validate. Has the zero vector, it's non-empty, it's closed under addition, and it's closed under scalar multiplication. If we can show that that's true for the way we've created this null space definition, then in fact it's a subspace. Here then we need to say that the subspace, or to sort of keep us grounded, the subspace must satisfy three properties. One is that this null space contains the additive identity. So we have a non-empty subset. And one way to do that is, let's now just play with the additivity property of the zero vector. So we can write 0 all sorts of ways, and one easy way is to just say 0 plus 0. Is it not? So here is the additive identity in V. But what do we know about a linear map? It satisfies additivity, doesn't it? So now we can split this t of 0 plus 0 into two pieces. We can say, oh, that's t of 0 plus t of 0. By the additivity property, of a linear map. But now that says that we have 2 t of 0 on the right. And now we have what? A vector, that's t of 0, equal to 2 times that same vector. How does that happen? Only when it's equal to 0, right? So we have something equal 2 times that something. Well, when is that true? When that something is 0. So now we've shown that t of 0 is equal to 0, where this 0 is an element in the codomain W. This is the 0 vector. Where does it live? That's in the domain, which is V. And that's what we were trying to show, that the 0 vector belongs to the null space. Any vector that when operated on it by t maps to the 0 vector is in the null space. And here we've shown that the 0 vector is actually in that null space. So we've shown property 1. So 0 is in the null space of T, where this 0 is in V. There's property 1. Question?
Why did you make T of 0 equal T of 0 plus 0?
So why did I make T of 0 equal T of 0 plus 0? Because I knew I wanted to come up with this sort of contradiction of a vector equaling 2 times that same vector so that I could put that vector equal to 0. So I didn't show it, did I? But I sort of worked both ways. I started with t of 0 and I said, how can I make t of 0 equal 0? Well, then I went back and I said, oh, what would cause that? Well, if I made it 2 times t of 0, then that would force t of 0 to equal 0. And now how do I make 2 of t of 0 appear? Well, I can write 0 a lot of ways. Let me write it as 0 plus 0. So I sort of went from forward and backward to work to the middle. And so, yes, sometimes when you're reading a proof, you're going, well, now how did that magic happen? Well, maybe it didn't happen by magic. Maybe it happened by an argument of thinking from front and back and meeting in the middle. And now when it's written, they're going to just write it in the forward direction. And so making that connection may have appeared to be somewhat out of thin air. But that's developing our mathematical maturity. So there's property 1. Property 2 is that we want this null space, all of these vectors that are in the null space, to when we add them together to belong in the null space. So the null space needs to be closed under addition. So now let's just assume that we have 2 vectors, u and v, that are in the null space of our linear map. That's a given. So now I can say, well, t of u plus v, since I'm going to look at their combination, I need that to be in the null space, but by what property of our linear map can I now use? Additivity. So now I can say, oh, that's the same as t of u plus t of v. Well, I assumed that u was in the null space, and I assumed that v was in the null space. I now know what's on the right-hand side. I now know that this is 0 plus 0, which is 0, which is an element of w, and now I know that the sum of u plus v is in the null space, because that vector mapped to the 0 vector in w. Therefore, u plus v is in the null space of t. And there is a verification because I arbitrarily picked u and v from the null space. I didn't pick specific ones. I said assume u and v belong to the null space. Now it could be any u and any v in the null space, and their sum maps to the null space of t. Third property, closed under scalar multiplication. Again, let's just pull one of these vectors out of the null space hat. So now we'll say given u is in the null space of t, and let's just assume or select some constant in our field. Let's look at t of au, but this is a linear map, and that gives us the opportunity to use what? Homogeneity, which now I can say, oh, that's a times t of u. Whew. Now I know t of u, that was giving me 0 because that's where I picked u. This is now a times 0, which is 0, which was in the codomain w. And now if au, when operated on by t, gives you the 0 vector, you now know that au is also belonging to the null space of T. And we've now satisfied all three properties, so we can say that the null space of T is in fact a subspace of what vector space? V, the domain. So it's mapping to the zero vector in the codomain, but it's actually the null space is in the input vector space. Now let's talk about the injective map. And here when you start talking about the injective map, you might start thinking about, oh, this is maybe related to or associated with the null space. So here, how it's associated is this is now, or if somebody says I have an injective map, if that doesn't seem to sort of resonate, say, oh, this is a one-to-one map. One vector in the input space is uniquely mapped to one vector in the output vector space. That's what we mean by one-to-one. And this injective map has a null space connection. And what we want to do now is start to establish that via a definition. Given T, that's an element of this set of linear maps going from V to W, that's a given. So we're given a linear map. If whenever U and V belong to our input vector space V, and T of U maps to the same output vector as T of V. So T of U is equal to T of V. Whenever that implies U is equal to V, that's our definition. Then the map is said to be injective. So given U and V, and the fact that when T of U equals T of V implies U is equal to V, then that's an injective map. That's what we're meaning by an injective map. Now recall that a consequence of having a linear map, T of U maps to a unique vector in the output vector space, or in the codomain. T of U already selected a unique element in W. So this linear map, if you operate on a vector U, that's going to go to one point in W. It's not going to go to multiple points. It's just going to go to one point or one vector. That's what we're meaning here. T of U goes to one vector in W. In an injective map, pardon? The question was, did we prove that already? It was basically just stated. And that's really just kind of a fact. If you now have a linear map and you apply that linear map to a vector, it's going to go to the same point every time you apply it to that same vector. That's really all it's saying. You give me 1, 2, 3 and apply t to it, that's going to go to some output in W, whatever that output is. Okay, let's go back. Let's do 1, 2, 3 again. It's going to go exactly to the same point. It's not going to say, oh, today I woke up, I feel like going a different place. That would violate the linear map property. That's it. So it's not that deep. It sounds like, well, we need to show that or verify that, but it's really not even necessary to show or verify. It's just you give me a linear map and apply it to a vector, it's going to go to the same point every time. So it's going to go to a unique point. What gets interesting is when we start applying it to other vectors, u, v, w, whatever. So now an injective map, in an injective map, only a single element of the domain V maps to that unique element in W. So here's something maybe to keep in mind, is don't read into that last comment that T of U already selected a unique element in W. Don't assume that that means that there's only one vector that gets you to that W, or that vector in W. So we're not saying that. So there could be T of U getting you to a Z. There could be a T of V getting you to that same Z. That's not what we're saying here. We're just saying that you give me a U, I'll take you to Z. You give me a V, I'll take you to Z. Give me that U again. Well, I'm not going to go to a Z prime. I'm going to go to that same Z. Is that clear? So that doesn't mean that I can't go to the same point in W. That's sometimes we can read that into that statement, and that's not what's trying to be said by that statement. So make sure it's clear there. So an injective map, in an injective map, only a single element of V maps to that unique element in W. That's our one-to-one relationship. There is a one-to-one there's a one-to-one relationship between elements of V and W for T when T is injective. Or the picture now, you're going to get tired of these clouds, but they're different every time, right? Here's V, and here's W, and we're mapping between those with T. You give me a point here, that's going to map to a point there. You give me a unique point in V, and that's going to go to another unique point in W. You give me an even different point in capital V, that goes to another point in W. That's an injective map. So, what might that look like? Suppose that we had this, let's say X is just real, and its codomain is the following. Let's say that now we have this. There's f of x. In this case, for example, something that maybe looks like that might be this exponential. And one way to think of that is now how would you sort of define that you give me a unique x, or give me a unique x, I go to a unique y or a unique f of x. One way to check that would be to draw a horizontal line. That's supposed to be horizontal. It only crosses that function once. It doesn't cross it multiple times. So here, if this is, let's say, x naught, here is alpha, which is f of x naught. So each horizontal line and this is just a one-dimensional example, so you would have to generalize it to a higher order dimension if you were dealing with a larger input vector space or domain. Each horizontal line only passes through one point on f of x. So let's look at something that doesn't satisfy that. So contrast that with, that was a one-to-one map. You give me an x, I give you one y or f of x. What about a many to one map? What if this were flat and then it went something like that? Now, here you give me an x1, somebody else gives you an x0, and they map to the same point. So this is now a many to one example. This is not one to one, that f of x. So that's the contrast between an injective map and a non-injective map. Now, there's a strong relationship between an injective map and the null space, and that's what we want to try to cover. So there's a strong relationship between the null space of a map and whether the map is injective. Proposition 16 in chapter 13. Injectivity, here's sort of the label on proposition 316. Injectivity is equivalent to null space actually equaling the zero vector, or being trivial. So injectivity is equivalent to having a trivial null space. If you have a linear map that's injective, then its null space is trivial. So that's the label on proposition 316. Now here's the proposition. Let T be a linear map from V to W T is in fact injective, IFF, we're texting now, so we're trying to be efficient with our character strokes or keystrokes. This is really just if and only if, the notation for that. So T is injective if and only if the null space of T is the trivial vector or the zero vector. So now, how do we show an if and only if? Or this is a statement. We have a linear map T from V to W. We're saying T is injective if and only if the null space of T is trivial. How do we prove that? Whew. I have no idea what I'm doing here. Where did I go? Please come back. So what do I need to do? Pardon? Counterexample. So now if I'm trying, so this is given to us really. This is a true statement. We now have to verify that it's true, right? So we don't really need to worry about a counterexample here. But if I gave you on an exam and I said, prove or disprove the following statement, then you might be saying, let me look at some possible statements and see if any of those disprove this statement. And if none of them are, then you go, oh, I probably need to prove this. It's probably true. Here, we're told that this is true. So now we have to verify that truth. And it says T is injective if and only if the null space of T is the zero vector. Well, now that's really saying T is injective, or if T is injective, then the null space is 0. Or it's also saying if the null space is 0, then T is injective. So it's conditional in both directions. And we have to now show or prove that it goes in both directions, the conditioned statement. And that's how we can prove this. We can say if A then B, or if B then A. If we can show both of those, then we've proved this true statement, that it is an if and only if proof or statement. So that's what we want to do. The proof is going to be to prove an IFF. That's not a BFF, but it might be. Might be your BFF after this class. You might have a lot of BFF propositions. Let's move on. So here we have this IFF, if and only if. To prove an IFF, we have to show implication in both directions. So we need to show that the conditional holds both ways. If A, then B. If B, then A. So first, let's assume one of those parts or pieces. So now let's assume that this linear map is injective. We know it's a linear map, so assume this linear map is injective. Now, let's just pick a vector in the null space of that linear map. And this is arbitrary. Let's just pick a V. So now we let V belong to our null space. what does that say? Well, that says then that T of V is equal to what? 0. We know that because V is in the null. That's what we said. We said let V be in the null space. So now T of V is equal to 0. And now we can remember what we learned in a previous proof. Where we were proving proposition 314. That was concerned with the null space being a subspace. And the very first property of something being a subspace, it has to contain the 0 vector. So we know that the 0 vector belongs to the null space of T. So let's use that. We know that T of V is equal to 0 because V was in the null space of T. But we also know that the 0 vector is in the null space of T. So now we know that T of 0 is equal to 0. And where are these zeros? Where's this 0? Remember, 0 is overloaded. So this one's in V. Where's this one? So that one's in W. Now, what do we know? T of V, what was that equal to? 0. But in the previous line, we saw that 0 is also equal to T of 0. But what did we just say about T? We said T is injective. And what does it mean when T is injective? Then the vector in the domain has to be the same, doesn't it? So now, by definition of this map being injective, this is now saying that 0 and V are the same, because we assumed T was injective. By definition, of a map being injective, we now know that V is actually equal to 0. And V, we picked it just generically. And now we've shown that it has to be the 0 vector all the time because this map is injective. Therefore, we have shown 1/2 of the proof. We have shown that T being injective implies that the null space of T is the 0 vector. That's the only thing it can be, because the injective map is unique, or 1-to-1. So if we end up at 0, there's only one vector to get us to that 0. And if we pick that vector to be V, well, that vector now is actually the 0 vector. So that was going in one direction. If T is injective, then the null space of T is the 0 vector. Now let's condition our statement on the first one. If the null space of T is the 0 vector, let's show that that creates a linear map that's injective. So now assume that the null space of T is the 0 vector. Only contains the 0 vector, or This is what I'm calling, we have a trivial null space. So now let's let u and v be coming from our domain, and let's assume that t of u equals t of v. That's an assumption. Yes?
Do you refer to a trivial null space as the null space that only contains zero?
Yes. So when I say a trivial null space, the question was, when I say a trivial null space, does that mean the only vector in that null space is the zero vector? Yes. That's what I'm meaning by a trivial. It's trivial because it only contains one vector. And the null space has to be a subspace. And so what's the simplest null or vector space or subspace? It's the zero vector. And so that's the trivial null space, is what I'm using to denote that. So now let's let u and v belong to the domain and assume that t of u is equal to t of v. So now we can say 0, and now it's probably this forward-backward thing again. But 0 we can write as t of u minus t of v. If t of u equals t of v, then we can take their difference and get the zero vector. But now what can I do? I can use additivity, can't I? I can now say t of u minus v by the additivity property of my linear map. Now what does that say? This vector that t is operating on this vector, what do we know about it? We now know that it's in the null space of that linear map, right? Because it maps to 0. So now we know, so u minus v belongs in the null space. But what did we assume? We assumed that the only vector in our null space is 0. So what does that tell us? Well, that tells us that u minus v is the 0 vector. This says then that u minus v is 0. That's the only vector that it can be. Therefore, u is equal to v. And what have we shown? Therefore, t of u equaling t of v has actually implied that u is equal to v. And this is actually the definition of an injective map. So there we've proved the other direction. So now we have shown that if we start with the null space of t being the 0 vector, then that linear map will be injective. And we've now proved both ways. So therefore, t is an injective map if and only if the null space of t is the 0 vector. So let's look at a non-injective map, or start to get a feel for what that is relative to null spaces. A non-injective map we can think of again pictorially. We want something in V to map to something in W, but we want many points in V to map to one point in W. And the way that we can make that happen is if we have a large number of vectors, a subspace in V in our domain that actually map to the zero vector. If we have a non-trivial null space, that will allow this to happen. So note, a null space of T is non-trivial for a non-injective map. Example. Suppose T has a non-trivial null space. And to help us, let's let W1 be the result of mapping V through this linear map. And suppose that T of U actually maps to 0, where let's assume U is not the zero vector. U is now a non-trivial vector. Or that is, U belongs to the null space of T with U not equal to 0. What does that tell us? Well, now if we let Z, a new vector, be V plus U, and we know that it's different from V, don't we? Because U is not equal to the zero vector or the additive identity. So Z is different from V, but what do we know about the codomain result of having Z mapped through T? Z is now a combination of V and U. So this is now T of V plus U. T is a linear map. And what do we know about this? We let T of V equal W1. What's T of U? And what have we just shown? Now we have, therefore, T of Z is equal to W1, which is also equal to T of V, but that does not imply that Z was equal to V. Because Z was definitely different from V because it was V plus U, and U was non-trivial. So now we've shown that T is not a one-to-one map. So if you have a non-trivial null space, do you see that you can pull vectors out of that non-trivial null space almost at will to give you the same point in your codomain as another vector might produce? So now if you have a non-trivial null space, then the map is not injective. It's no longer one-to-one. It's many-to-one, because you can have many different vectors that map to the same point. And so we've talked a lot about the null space, which gets us nowhere. It gets us to the trivial vector. Let's talk about the range space the next time, which gives us a lot more places, hopefully. So we don't have a name for the many. Yes, we do. It's non-injective. So the name of our many-to-one map is a non-injective map, okay, by default.